Okay, hello, I'm Martin Folger from IRIS, and I will talk about the Semantic Scene Map. As we've seen in the introduction, Rossini has several layers, and the Semantic Scene Map is in the perception layer between the sensing layer and the cognitive layer. The sensing layer, in this case, what is relevant for us are the cameras, RS4 cameras, which provide, in this case, gray images, and they also provide depth images, which we need as input. Then the semantic scene map performs an object detection and separately a human skeletonization algorithm. And it also uses the depth information of the cameras to place the detected objects in a 3D. Whereas the algorithms work in 2D, the result will be put in 3D using the depth information. The result of this will then be passed on to the cognitive layer. So here we see this as an example. So the object detection is this kind of algorithm which recognizes objects in the scene and places a box around it and labels it with the thing that it has detected, in this case, person. The skeletonization algorithm works a little bit differently. It only works with persons, and it not only detects it's a person, but it actually detects the human skeleton, the joints, as you see at the bottom left. On the right, you see this both combined. The yellow is the box and the skeleton you see as well in 3D. Here the limbs are made thicker, but this is just a way of, does not come from the algorithm, but it's just a visualization thing. Okay, now this is about how this is actually implemented. So in Rossini, we use the ROS operating system, the robot operating system, which allows you to have lots of different software nodes, which are independent software computer programs which read information from the pool of topics and then process them and create their own ROS topics, which is again a data stream which can be subscribed to by subsequent programs and for further processing. So in this case, at the bottom you see camera 1 and camera 2. This is just an example. It could be 3 cameras or 1 camera. So you can have multiple cameras. Each of them create and publish to the ROS network, to the ROS framework, grayscale images, depth images, and much more, like camera information. There's a huge number of ROS topics which is published to the network. The 2D skeleton is one of these algorithms that I explained before, which reads the information it needs, mainly the grayscale images at this stage, and applies the algorithm, and then publishes various topics. For example, it publishes the same image again with the skeleton superimposed. This is only for visualization, but it also publishes the skeleton as a number of coordinates, as a list of coordinates, and publishes into the ROS for further processing. The same happens with 2D object detection, and the same happens then again for the camera 2. The next step is the 3D skeleton and 3D object detection nodes, which subscribe to the 2D information already obtained. They subscribe to the depth image and place the 2D coordinates into a 3D scene and publish that information again in the ROS framework. This allows for the results from different cameras to be fused into one final skeleton or object detection box. This final result gets published and will be used by the cognitive layer, or also it can be used by the visualization of ROS to inspect the results. Okay, here we have an example from the Schindler use case. This is a test scene of the Schindler use case with a human being working on a elevator button panel in collaboration with a UR10 robot. So here you see the skeletonization applied. On the next one, you see again the skeletonization applied, and as I said before, through publishing the skeleton and then further processing it, in the end you see this final result. This is the 3D human skeleton. And again, as well, a 3D representation of the robot. the robot information in this case does not come from the cameras, but it is actually reading the robot coordinates directly from the ROS framework. The robot positions are also published as information in the ROS framework. This can be then be combined in the 3D scene to give you this final result, which is what is being used by the cognitive layer. And here you have a similar example, but instead of the Skeltonization, you have the object detection algorithm detecting a person, the UR10 robot, and the elevator panel. And this is the whole final result, also represented here as the yellow box for the object detection. This would be the person box. Inside you see the skeleton. And here you see three frames of reference, the world frame of reference, which is used to publish this final result. But initially the skeleton and the box are calculated in the reference frames of the cameras, and they have to be combined into a world reference frame, which is then used higher up by the cognitive layer. Okay, this is all from the Semantic Scene Map.